Alright, class, let's revisit something. Let's look at straight lines. So, straight lines, Mr. Butler, how are we revisiting that? We've been doing curves the whole time. But there was way back when we started talking about, like S of t and V of t and A of t, and we started saying things like, is it speeding up? Does it speed up or does it slow down? And a lot of that stuff, when we were saying speeding up, where two things were moving in the same direction, both your velocity and your acceleration, but if your velocity and your acceleration are fighting each other, then you start to slow down. So this is that idea of something moving horizontal or vertically only. But now, as we revisit it, we're not just going to be measuring rates of movement and stuff. We're going to actually look at displacement and distance traveled. Displacement, so how displacing, and distance. And those are very close in meaning, but also very significantly different. So let's take a look at them. We looked at this, earlier. We said if we had the position function, velocity function was the derivative of that, and the acceleration was the second derivative of that. So then that goes to say that if we worked our way backwards, you have S of t and you're working your way down to V of t and then A of t, you can also work your way back up. So this is like doing derivatives, but if we were to do integrals with respect to t, that's going to move us back up this way. And now we can do integrals. We have that skill, so let's apply it. Let's look at these first things. So it says find v of t given that a of t and v of 0. Now why does it matter that we have this 0? That's going to help us solve for the constant, which is that plus c part. So let's work our way through this. If we know a of t equals 4t minus 6, then v of t is going to equal the antiderivative of a of t, dt, but we're going to have plus some constant here. So what's the antiderivative of a of t? Well, if it's 4t minus 6, so what's the antiderivative of 4t minus 6? Well, this 4 is a constant, so that stays there. T to the first power becomes t squared over 2. And this 6 is going to become 6t. And we still got the minus. This 4 and 2 simplify. We got 2t squared. And of course the plus c. So here's our v of t equals. So velocity is going to be equal to 2t squared minus 6t plus c. We know that if t equals 0, velocity equals 3. So 3 is going to be our v of t. Then we're going to plug in 0 for these other parts. 2 times 0 squared minus 6 times 0, and then plus c. Doing some simple algebra here, those go to 0, so 3 equals c. So what does this tell me? Plug that in. I got to plug that value for c in up here. So my final v of t equals 2t squared minus 6t plus 3. Check, done, simple. Let's do it again. All right, so slightly different here. We got some trig going on and some algebra, and our initial velocity is 0. So let's see how this works for us. We know that we need to take the antiderivative of sine of t plus 2t. I'm going to treat this actually as two antiderivatives. Let's give ourselves some space to put in the dt in there. So sine of t dt plus the integral of 2t dt. Let's see what happens. Antiderivative of sine. Well, the derivative of cosine is negative sine, so that means there's a negative missing. So negative cosine of t plus this 2t to the first power becomes 2t squared over 2, and the 2 over 2 is really just 1, plus c. So this is my v of t. So what's the problem? I have this c over here that I got to somehow solve for. I know that v of 0, so that means when t equals 0, velocity is 5. So velocity is going to be 5. And we got negative cosine of 0 plus 0 squared plus c. So I'm going to plug in that 0, this 0 right here. Cosine of 0 is really 1, so that's negative 1. 0 squared is 0, so that goes away. And then we got plus c. So negative 1 plus c equals 5. Well, that's easy enough. Simple algebra now. 6 equals c. So the final answer, what do we got? V of t equals negative cosine of t plus t squared plus 6 is our value for c. Check done. This is nice. This is very nice. Very simple. Okay. So let's get complicated then. We got two things. It's really not complicated. It's just different. We got two things here. Distance and displacement. So a real simple diagram. Let's say I start here at point A and I finish at point B. I really only traveled a little bit. Because if I travel 80 miles to the right, then I travel 60 miles to the left, I'm going to finish at a difference of 20. That's called my displacement. It's kind of more like your location. You started where, ended where, how far difference was that. But distance is going to be a little bit different than that because we traveled 80 and then we traveled 60. So we traveled 140 miles even though we ended up only 20 miles from where we started. So can they be equal? Yes, they can, but here's the catch. This top movement here, we consider this like a positive movement, and this bottom movement, this would be like a negative movement. And those negative movements are what change our displacement and distance. So if we didn't have any negatives, if we only had positive, then they're the same. So if the movement, which is really our v of t, is positive only. So then what does that mean? How is one thing equal to another, but really it doesn't matter if they're just positive? That's called absolute value. So distance in reality then is the absolute value of displacement. And if displacement was already positive, then these are equal and you don't have to really make it positive. Okay, so let's do this. Oh, we just figured this out here. Absolute value is distance. When does it not matter? When you were traveling only positive directions. Then we get the same thing. So let's do this. Displacement from A to B of V of t, distance from A to B of V of t. So we have V of t here, and it's asking us for a couple of things. Displacement versus distance. I'm going to show you why one is easier than the other. But let's just start out with displacement. Displacement is kind of what you would expect. The integral from 1 to 7, because that's our interval here, of t squared minus 7t plus 10 dt, of course. So it's simple antiderivative with the upper and lower limit. And the antiderivative is t cubed over 3. Then we got minus 7t squared over 2 plus 10t. So we're going to plug in those two values there. That's going to give us 40, whoa, not 49. What is 7 cubed? 7 times 49. I think that's 343. Is it? 49 times 7. 9 times 3 is 27. Ooh, so let's see what that would be. 7 cubed is equal to 49 times 7. Oh, it is 343. Yeah, it's 343 divided by 3. And then we got minus 7 times 49 over 2. and plus 10 times 7. So that's our top. Should have written up here top. Then we got to do minus bottom. We're going to crowd some of the space here. And that's going to be all the bottom terms. So here's all our top terms. Plug in 1. Plug in 7. Now we're going to plug in 1. We got 1/3. That was easy because 1 cubed is just 1. Minus 7 times 1/2, or 7 halves. And then we have plus 10 times 1, which is really just plus 10. Okay, that wasn't too bad. Let's simplify some of this. I know you're thinking, wait a second, Ms. Speller, you just said this was easy. It is easier than the distance, kind of. So let's see what's happening. We got 3/43 minus 1/3. That's going to give me 3/42. Next, I have 7 times 49 over 2. That's really 343. I figured that out a moment ago. Minus negative 7/2. So that's really plus. So that's going to give me negative 343 plus 7 is really minus 336 over 2. That would come out evenly. Then we got plus 70. This is a plus 70. Then we got minus 10. So that's going to be plus 60. Now we can simplify that. We'll get a pretty straightforward value. But I'm going to leave it there for a second. Because displacement is the integral. That's not a problem. But the difference then is, how do I deal with this absolute value? Well, when you have that absolute value here on the inside, what that's going to take, what that's going to do is all areas are positive. And when we talk about positive areas of a typical integral that's moving from left to right, that means they are above the x-axis. So let's take a look at this graph, this function here. We got t squared minus 7t plus 10. So I'm going to have my y equals, and I'm just going to start out with that. Squared minus 7 times the variable plus 10. We're going from 1 to 7, so I'm going to go back to my window. Change this from 1 to 7. And let's see what we have. Well, we probably need to change our y values. Well, let's go down to like negative 5. Let's see what we get. Okay, so there is our picture. So the interesting thing is, I'm going to throw this in here just for a second. Actually, you know what? No, I don't want to do that. Let's take that back. I'm going to make two graphs here. The second one, I'm going to do the absolute value of the first one. And we'll have them both running at the same time. So that's the first one. Now let's look for the second one. The second one would be, we got math, then num, and then we need the absolute value, which is 1. And then we're going to put in the y1, which I can do under the vars menu, yvars, function, y1. There we go. All right, so that was pretty quick there. So now I got two graphs. What's the difference between the two? Just this bottom piece gets flipped up to the top. So now I'm going to take this whole thing and put it over that one. And so here's what's happening. If I take the absolute value, it's going to flip that piece up. You know what? Let's do this real quick. Let's go back here. Y equals. We're going to turn off the first one. Get this graph. So there's what it looks like when it's flipped. Now you guys are going to see something pretty cool here. Oh, what just happened? That's what I wanted. There we go. Okay, so now that's when it's flipped. When it's not flipped, it looks like this. Ah, look at that. It's like an animation. So when I take the absolute value, it's going to take that bottom area and flip it up to the top. So how do I deal with that? You know, without a calculator, how do I deal with that by hand? Well, there's a couple of things. I need to figure out when is this negative. And it's negative when it crosses that axis. So do I know what this value here and here is? I do from the graph, but could I figure out that from the function? I could if I just factor it. If I factor this function, it would be t minus 2 and t minus 5. So that's where those two values are going to be at 2 and 5. So from 2, so that's 2, 4, oh, something looks wrong. 2, 4, 6, 8, 10. Going from 1 to 7. Oh, that's because this is 1 right here. And then we got 1, 2, 3, 4, 5, 6, 7. So that's where we're going. So we're going from 2 to 5. Okay, so now that I'm looking at this, now when we put the absolute value in there, that means that we're going to have to split that area at 2 and 5. Okay. So how do I deal with that? In order to deal with that, I need to split this into 3 zones. We have like a zone A, a zone B, and a zone C. So zone A, it's going to be just a regular integral. It's not flipped at all. So that's going to be from 1 to 2. And that's just the regular graph here. T squared minus 7t plus 10. Zone C is very similar. Regular graph, but this time we're going from 5 to 7 of t squared minus 7t plus 10. dt, of course. But we're running out of space here. But the zone B in the middle, it's flipped. That's this piece here. This is flipped. So because that's flipped, I got to make all those negative. So that's going to be negative t squared plus 7t minus 10. And we're still going from 2 to 5. Okay, so let's figure this out. Let's calculate it. If I'm going from 1 to 2 for this integral, let's take the antiderivative. That's going to give me t cubed over 3 minus 7t squared over 2 plus 10 t. And that's going to be the same thing. I'm going to evaluate that from 1 to 2, but then I'm also going to do the same from 5 to 7. But then I'm going to need a third zone, so we got like our A zone and our C zone here, because it's that same function, t cubed over 3 minus 7t squared over 2 plus 10t. Let's look at the middle piece though. That's going to be the opposite sign. So we got negative t cubed over 3 minus 7t squared, or plus 7t squared over 2 minus 10t. And that's going from 2 to 5. So I would need to add up those 3 areas. Now it's not hard from here. This is mostly just algebra, and you can see now why it's more difficult. You thought this first one was difficult with all that calculation. Now I got to do this calculation 3 separate times and then add them all together. That's a lot of calculation. Or yeah, because you got a top and a bottom 3 separate times. That's like 6 different calculations instead of 2. I'm going to leave that one there, but I'm going to show you on your calculator how to check the answer to see that you would get the correct answer. So let's find the area of this. So I'm going to do second calculate area, which is 7. And we're going to start at 1, and we're going to end at 7. Let's see what we should get with our answer. It looks like the answer is about 15.000572. So it's probably going to be 15. I'm telling you right now, it's pretty sure this is going to be 15. Because the calculator is just an approximation. But the total should come out to 15. So work through those fractions, see what you can do. Let's look at more of this calculus stuff. So here's the general idea broken down. And you probably saw this, hopefully, on your calculator. Now notice that you can do this without doing it from the graph, but you can just do it straight from any screen if you use the fnint function, and this is what you would type in. But I definitely prefer using the graph. Notice here that we had to split this into 3 zones, A, B, and C. So that's exactly what we are doing. Whereas over here, it's just from 1 to 5. It's the whole way. So you either have positive, positive, and negative area, or when it's absolute value talking about distance is positive, positive, positive. So let's try using that idea. Given an object moving in a straight line, a of t equals square root of t, v of 0 equals negative 18, t equals 0, and t equals 16. Find v of t and the displacement and distance of the object. Oh my goodness. There's so many things going on in this problem because first of all, we start with a of t. So 1, we got a of t, but we're going to use that to find v of t. Plus c. We got that plus constant. Then we're going to take that once we have that thing and we're going to try and find the integral from 0 to 16 of v of t dt. And this is going to be our displacement. And then remember that the integral from 0 to 16 of the absolute value of v of t is going to be our distance. Okay, so let's go through this. We got like 3 stages to work through. The first thing to do is to figure out what is the velocity based on this acceleration function. So if we know that that's acceleration, t to the 1/2, let's take the antiderivative and work towards velocity. So t to the 1/2, the antiderivative is going to become t to the 3/2 when you add 1 to that power over 3/2 plus c, of course, but that's really 2/3 t to the 3/2 plus c. And that's our v of t. But we know that when we plug in 0, that's going to be negative 18. So if I plug in negative 18 over here, I can plug in 0 for the t. 2/3, 0 to the 3/2 plus c. Well, this 0 kind of creates a 0 for this whole term, because 0 to the 3/2 is 0, times 2/3 is 0. So negative 18 then equals c. So my official velocity function is going to be v of t. Let's write this in some vibrant color. V of t is 2/3 t to the 3/2 minus 18. Now for these calculations, we're going to be looking at this from a graphical standpoint. So we're going to use the graphing calculator to see what we need. But the general idea to figure out those breaking points between 0 and 16 would be to figure out when the function actually equals 0. I'll show you how to do that algebraically as well. Just a quick note, there should be a dt right here. You didn't even notice that. Hopefully you did. So let's do the displacement. That is the integral. We'll do this in purple. That's going to be the integral of 2/3 t to the 3/2 minus 18 from 0 to 16. Okay, so if I were to take the antiderivative of this, that would give me 2/3 times t to the 5/2 over 5/2 minus 18t. And we're going to calculate that from 0 to 16. I could do this one by hand. So let's see what we can get here, just for some good practice. So we got 2/3 times 2/5 times t to the 5/2 minus 18t from 0 to 16. Okay, so we're going to do our top minus bottom, but I want you guys to kind of use some foresight here, looking ahead. And we have hindsight and foresight. Look ahead, predict. When I plug in 0 for the bottom pieces, that's going to be 0 for the first term, 0 for the second term. So that's really just a 0. Do some shortcut for your problem solving. Then all I really need to calculate is the first one, which would be 4 over 15 if I combine those fractions by multiplying. And then 16 to the 5/2. Well, the square root of 16 is 4. So we're going to have 4 over 15 times 4 to the 5th power. Whoa, what would that be? That's a huge number. That's going to be 16 times 16, because this is 4 squared times 4 squared times another 4 to the 1st power. Okay, well 16 times 16, I think that's 256. So we're looking at 256 times 4. Big numbers here. 4 times 6 is 24. 4 times 5 plus 2 is 22. 4 times 2 plus 2 is 10. 1024. So this equals, and then times another 4. Oh my goodness. Then we're going to divide that by 15. 4 times 4 is 16. Then we got a 9, a 0, and then 4 times 1 is 4. So this equals 4,096 divided by 15. And no, that is not going evenly. So that would be as simplified as it can get, maybe? Yeah, that's as simplified as that gets. That is crazy. So distance. What's the difference with distance? We got to take care of this absolute value. Well, let's take a look at the graph and see what's happening. So if I were to look at this graph, I'm not going to look at the absolute value of it yet. But let's look at the original. It was, what was v of t? 2/3. So 2 divided by 3. Not 2 times. 2 divided by 3. Times our variable to the 3/2 power. So that's going to be to the, and I got this in parentheses, 3/2. And minus 18. Now our interval here is from 0 to 16, so let's go from 0 to 16. Not sure what our numbers need to be there, but let's take a look and see what we got. Okay, so we definitely have some negative and we definitely have some positive. So I need to expand my positive and negative there. Let's say I was going not down to -5, but negative, I don't know, how about negative 20? No, how about negative 15? Up to positive 15. Let's see what that gets us. Okay, I almost got it all in there. So there's our function, and that's for the most part good. That's what we want. I'm going to go all the way down to -20 up to positive 30, it looks like. And I'm going to change my x scale to counting by 5s just to clean up the picture a little bit. And we're going from 0 to 16, so let's go all the way down to -20, and let's go all the way up to 30. Now I got a full picture in here. And even counting by 5s. Whoops, I wasn't supposed to count the x's by 5s. I'm supposed to count the y's by 5s. So that means to go down to here where it says y scale. If I put in a 5, that means it's count every 5 units. There we go. That looks a lot cleaner. So this bottom piece here, this is going to flip up to the top. So if I were to graph both of them, we got two pictures here. Let's go ahead and throw these both in here. Here's one. And then the second one is if I graph its absolute value. So I'm going to graph the absolute value now. I'm going to turn off the original one so I can see the difference. There we go. So that flipped up to the top. I'll layer these over each other. Now let's put them together and take a better look at them. Okay, so there we go. Now if I kind of fade this one out, you'll see what happened. It was below the graph, and now it's above the graph when we take the absolute value. So it originally was below, now it's above. So if I want to take the integral of this piece, it's going to give me something significantly different. So the key is how to know that difference. It's just using the absolute value. So if I go back to my calculator, now I'm going to take second and calculate this area, so that's 7. We're going to start at 0 and go all the way up to 16. So this one is the absolute value. It's just going to be doing the top piece here. And that's about 179.46667. So about 179.46667. And so this is the integral from 0 to 16 of the absolute value of v of t. Whereas the other one was this other number. So let's see what that had originally gotten us. So now if I go to y equals, I'm going to turn on the top one, turn off the bottom one, go to our graph, and now we can calculate this area, second, and then calculate the integral from 0 to 16. Should be a lot less than that. That gives us about negative 14.93334. So this should have been negative 14.9334, and that's really 0.9333 with a bar. So where are we missing this? Well, what's going on? Why do we have negatives, but it's not coming out? We have 2 to the 3 halves. Well, I'm going to have to take a look at that and come back to it, but we'll answer that in class. Of course, you guys can see if I typed it in inappropriately into the into our function. Oh, I think I know what it is. Let's take a look. No, that should be right. 2/3 times x to the 3 halves minus 18. Well, I'm not sure. That looks good for the most part, but we'll have to take a closer look at it and see where our calculations are a little bit off. All right, let's take a look at the last number here, last problem. Okay, so a subway train accelerates as it leaves one station, then decelerates as it comes to the next station. So look at this. We start out at 0, then we get faster, faster, faster. Here in the middle, we're going about 44 miles an hour. And then we decelerate when after about 60 seconds, now we're back at 0. So it's asking us find the distance the train travels every 5 seconds interval. So distance, remember, distance is rate times the time. So if we're talking at 0, how far did we go? So now this is going to be kind of an approximation. So if we start out at 0, how far did we travel? We traveled 0. But between 0 and 5, at 5 here, I'm going 15 miles an hour. So if this was a perfectly linear graph, let's plot this real quick. So I'm going to plot this. And I'm going to do this purposely where let's kind of take this, fade it out a little bit, use a light gray. So I'm going to take this and pull it down. I'm going to use these as my spaced out intervals here. Take that one back. We're almost there. We got a couple more here. Now I notice that the highest my speed goes is about 44. So I need to go up to, let's say that this is 50. And then we have, so we can go by like tens here. So we would have about 10, 20, 30, 40, and how about that's 45? We'll max out at 45. So this is 45, then we got 40, this would be 30, 20, 10, and 0. Okay, so at 0, we're right here. But then at 5 seconds, we're at 15 already, so we're all the way up here. And then for the next one, we have 10 seconds, we're at 33. Super fast. That was pretty fast acceleration there. And then at 15 seconds, we're at 42, so we're already getting close to reaching our top speed. And then 20 seconds, we're at 44, 44, 44, 44. And then now at 40 seconds, we're back down to 43. 45 seconds, we're at 38, so we're starting to dip down a little bit more. And 50 seconds, we're down all the way to 24. 55 seconds all the way down to 8, so we're slowing down really fast here. And then 60 seconds back at 0. So down here across the bottom we got 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, and 60. So you guys are probably wondering, why do we need that picture? Well, when you have raw numbers like this and not an actual function, you got to use some numerical approximation. In order to do that, we have to calculate using either some type of box sum or a trapezoidal sum. So if I were to do this with trapezoids, let's do this in blue, and I'll show you with diagonal lines here. That means that I would be going from here to here, and from here to here, here to here, and this is, even though it's kind of jagged, it's still smoother than pure boxes. And I could find the area of each of these individual pieces. So this first one, it's a triangle, pretty much, and this triangle has, a base 5 by a height here. This goes up to 15. So that would be 5 times 15, or 75, divided by 2. For the next one, it's a trapezoid. So notice that we're going to have two heights. We have 15, and this next height would be, what are we at 10? 33. So that means we're going to do 1/2 15 plus 33, and then times this distance in between, which is 5. Then for the next one, it's going to be 1/2 the two heights, which is 33 plus the next one is 42, and all that times 5. So I'm going to put this 5 and this 1/2 together because that's going to be the same for each one. So I'll have 5/2 times, now this one's going to be 42 plus 44. Now these next four, or next, how many do we have in here? One, so this one we have, this is 44, 44, 44, 44, and then we drop down to 43. So then we start changing. But these three boxes in the middle, it's a straight box because it's flat. So that's 5 times 44. Then we got 5 times 44. And 5 times 44. Those are flat boxes. I don't have to do trapezoids for it. For this next one, I do need to kind of take the average height here. So that'd be 5/2 times 44 plus 43. And then for the next one, we go from 43 to 38. So that's going to be 5/2 times 43 plus 38. And then for the next one, between 45 and 50, now we got 5/2 times 38 plus 24. And then for the next one, we got 5/2 times 24 plus 8. And then the last one, it's all the way down to 0, so it's going to be like a triangle. And it's just 8 by 5 here divided by 2. So if you take that, that would give you 20. All right, so we have all this distance traveled. What's the distance traveled by the time we got to 60? That was 20. But if we're looking at this as accumulation, there's a couple of views we can take here. Let's clarify that. We can do this individual terms, or it can build based on the calculation from the last one. So I'm going to take a second, use my calculator to calculate all these values. I'm going to put them in this distance. Then I'm going to answer these two questions. Ready? All right. So I'm going to pause, and by the magic of video, you will see it happen instantly. So here's the numbers that I'm coming up with, and I want to show you guys something that I was hoping you might notice is kind of funny with the numbers. And it's really just a detail in units that we need to notice. So right here, you're looking at your time is in terms of seconds, but velocity is given in miles per hour. So we need to convert some of this distance. If this velocity is in terms of hours, but this time is in terms of seconds, then this times 5 here instead of multiplying by 5 seconds into hours, how many seconds are there in an hour? Well, there's 60 seconds in 1 minute times 60 minutes in 1 hour. So that really means that there's 3,600 seconds per hour. So we have to take each of these things that we see here, and we have to, I can't even think right now, we got to divide it by this number. Because this is kind of taking advantage of the idea that we didn't. So if we're traveling 5 seconds, how much does that equal in an hour? Well, that would be 5 over 3,600. So if for each of these numbers we just multiplied by 5 for each one, but we should have multiplied by 5 over 3,600. So I got to take each of these numbers now and divide by 3,600 all the way across. Just like that. Okay, so something else is happening here. I did each of these areas individually. Each of these numbers down here should be also divided by 3,600. I'm not going to take the time to do that real quick. But the distance, I treated this as an accumulation. So we started out with 0 accumulated distance. But then we get to the very end here at 1897.5 divided by 3,600. So let's see what that would calculate to be. So we got 1897.5. We're going to divide that by 3600 to convert this time issue that we just had. And now it's going to give us actual miles. So we traveled total 0.52708-ish miles. So about half a mile. So let's say 0.527. So total, this equals 0.527 miles. And that kind of makes sense. You know, if the max velocity that we were going was 44, and we started out at 0, and then we also ended at 0, that means we're averaging somewhere in the middle. It looks like our average is about 30 miles an hour. And if you're going 30 miles an hour for a full minute, that gives you about half a mile of distance. So that makes sense, kind of, if you can do some of the calculation there in your head. But so the general idea, though, is think about this. We're only traveling forward. We are slowing down, but our speed is always positive. So to find our total distance traveled, we just took the area. So distance is the same as the area, because that's why we take the integral. The integral talks about the area. Ooh, almost froze the video there for a second. So we're talking about distance equals the area under velocity. But we should say positive area, because when we're talking distance traveled, you know, we want to account for everything being positive. So that's why we do this calculation, and sometimes it's not a simple function. Sometimes you have to calculate all the areas. Now this one was tedious, a little bit long. You're not going to see that like on an AP test just for time's sake, but the concept would still apply, especially in a free response question. Alright, so that's all we have for this video. I hope you enjoy it, and we'll see you in the next one, number 32.